Okay, in this lecture we're going to begin our Chapter 3 material on second-order linear differential equations. And in section 3.1 we're going to talk about the simplest case of a second-order linear equation, namely working with homogeneous differential equations which have constant coefficients. So let's begin by introducing some terminology. First of all, we would define a second-order ordinary differential equation as any equation which can be expressed in the form d2y dt squared, so the second derivative of y, which is a function of t, is equal to f, some function, which depends on t, y, and the first derivative of y. So here the highest order derivative appearing is the second order derivative, hence we have a second order equation. And this function f is some given function. So as with our first order equations, we're interested in determining solutions. So what do we mean by a solution? Well, it would be any twice differentiable function, y of t, that satisfies that equation. That would be called a solution of this differential equation. And in this chapter, we're going to be working only with linear second-order equations. In general, nonlinear second-order or higher-order equations are very difficult, if not impossible, to solve in most cases. But linear equations have some nice applications and can be solved relatively easily. So in the event that this function f is a linear function of y and the first derivative of y prime, then our equation is said to be a linear equation. So in this chapter, again, we're only going to be working with linear second-order equations. And in general, we can write any second-order linear equation in what we call standard form, similar to standard form of a first-order linear equation. So it would have the form 1y double prime plus some function p of t times the first derivative y prime plus q of t times y is equal to some function g of t. And in the event that g of t, the function on the right-hand side, is equal to 0, then this equation is called a homogeneous second-order linear equation. Otherwise, so if our function on the right-hand side is anything other than 0, this equation is called non-homogeneous. So in Chapter 3, we're going to begin our discussion of second-order linear equations by restricting ourselves to homogeneous equations, which are a little simpler to work with. And we'll make another restriction in this first section, and throughout most of Chapter 3, where we will only be considering a second-order linear equation which has constant coefficients. So let us consider such an equation, second order, homogeneous, where our coefficients are constants. So here we have something like a y double prime plus by prime plus cy is equal to 0. So here homogeneous, meaning that right-hand side is 0, where a, b, and c are just some constants rather than functions of t. And our method for solving this type of differential equation is to consider a solution of exponential form, something of the form y equals e to the r times t power, where r is some constant that we need to determine. So let's see how this solution technique will work. If we are considering solutions of exponential form, say y equals e to the rt, then our first derivative, y prime, would be r times e to the rt, and the second derivative, y double prime, would be r squared times e to the rt. So if we substitute y and the first two derivatives into our differential equation, equation 3, we're looking for a y double prime plus by prime plus cy, which would give us a r squared e to the rt plus b times r e to the rt plus c times e to the rt is equal to 0 in order to be a solution of this homogeneous equation. And from this equation, we can factor out an e to the rt from each term, and we are left with ar squared plus br plus c is equal to 0. And of course, this exponential function, e to the rt, can never be equal to 0. Recall that the range of any exponential function is positive real numbers. So the only way for this product to be 0 is if our polynomial in parentheses is equal to 0. So what we are left with is a quadratic equation in terms of r, and we want to find the roots of this quadratic, which we could do either by factoring or making use of the quadratic formula. So this equation that we obtain by seeking solutions of exponential form, this equation ar squared plus br plus c equals 0, is what is called the characteristic equation for the differential equation 3. And notice that this quadratic has the same constant coefficients, a, b, and c, that we had for our constant coefficients in the differential equation. So just by looking at our differential equation, we can immediately determine what our characteristic equation is if we're looking for solutions of this exponential form. Now, in the event that this characteristic equation has distinct real roots, let's denote them as R1 and R2, so two different real numbers, then the general solution of this differential equation 3 is given by y of t, which is c1 times e to the r1 times t, plus c2 times e to the r2 times t. So that is, we take the roots that we find, r1 and r2, and we can substitute them into the form of the solution we were looking for. So we find two solutions, e to the r1t and e to the r2t. And the most general solution of that equation is then just a linear combination of those two solutions. Something of the form c1 e to the r1t plus c2 e to the r2t, where c1 and c2 are arbitrary constants. And it's not immediately clear why the general solution would have this form, but in our next section, 3.2, we will justify why the solution takes this form. So now that we know how to find the general solution of some types of homogeneous second-order linear equations, let's look at some examples of this. So in this first example, I ask you to find the general solution of each differential equation, and then describe how the solutions would behave as t becomes infinitely large. So in part A, I have this second order homogeneous linear equation with constant coefficients. So I know that my method for solving this type of equation is to look for solutions of exponential form. I want to assume that y has the form e to the rt power, which means that the value r would have to be a root of the characteristic equation 1r squared plus 3r plus 2 is equal to 0. And to find my values of r, I can factor this expression as r plus 1 times r plus 2 is equal to 0. Therefore, r could be -1 or -2. So we have two distinct real roots, two different real numbers for my values of r, which means that our general solution, y of t, is of the form c1 times e to the -t plus c2 times e to the -2 times t, where c1 and c2 are arbitrary constants. So we've constructed our general solution, and for the last part of the problem, we're asked about the limiting behavior of our solution, what happens as t approaches infinity. So as t approaches infinity here, we see that our function, y of t, will approach 0. Because these two roots that we found, r1 and r2, are both negative numbers, so these exponential functions both exhibit exponential decay as t becomes large. They both tend to 0, therefore the sum tends to 0. So let's look at the next one. In part B, we have the differential equation y double prime minus 2y prime minus 2y is 0. So again, it is second order, linear, homogeneous, with constant coefficients. And my technique for solving this type of equation is to look for solutions of exponential form. Y equals e to the r times t, which means that r has to be a root of the characteristic equation 1r squared minus 2r minus 2 is equal to 0. And in this example, we see that this can't be factored nicely, like in the previous one, but we can always find the roots of a quadratic by applying the quadratic formula. So here our roots r could be found by taking positive 2 plus or minus the square root of -2 squared minus 4 times 1 times -2 gives me a positive 8 all over 2. Or if I simplify this a little bit, I have 2 plus or minus the square root of 12. Now 12 is just 4 times 3, so taking the square root gives us 2 root 3 over 2. And so dividing through by 2, we are left with 1 plus or minus the square root of 3. So again, we have two distinct real roots, two different real numbers for our roots. Therefore, the general solution of this equation is given by C1 times e raised to my first root, let's say 1 plus the square root of 3 times t, plus C2 times e raised to the other root, which was 1 minus the square root of 3 times t. Okay. So here we have found our general solution, and again we're asked to determine the limiting behavior of our general solution. As time t approaches infinity. So let's look at each term here. For this first term, e raised to the 1 plus square root of 3 times t, our root is positive. So this first term is going to exhibit exponential growth, whereas our second term, e raised to the 1 minus square root of 3 times t, well, our root 1 minus the square root of 3 is negative, so that second term exhibits exponential decay approaching 0. So our first term is what is going to dominate our growth. We have exponential growth, and then we're multiplying out in front by some arbitrary constant C1. So depending on the value of C1, our solution, y of t, might approach positive or negative infinity, depending on the sign of C1. So what we've seen in these first couple of examples is that the sign of our root, R1 and R2, will determine our long-term behavior of the solutions. In particular, if both of our roots are negative, our solution will approach 0 because we have exponential decay of both terms. Whereas if one of our roots is positive, then we have exponential growth without bound, and our solutions will approach positive or negative infinity depending on the sign of the constant in front of that exponential growth term. So let's take a look at another type of example. In this next example, we're sort of working in the opposite direction of what we have been doing. Here we are asked to find a differential equation whose general solution is given as y equals c1 e to the negative 4t plus c2 times e to the 3t. So here we are given our general solution and we want the equation that it solves. So looking at our general solution, we can immediately see that the roots of the characteristic equation are given by R1, the first value, would be negative 4, and R2 is positive 3. So if we know the roots of the characteristic equation, we know what the characteristic equation is. Let me say the characteristic equation is given by r plus 4 times r minus 3, or if we expand, r squared plus r minus 12 is equal to 0. So once we have our characteristic equation, we can write down the differential equation that would have this as its characteristic equation. Here we had a 1r squared, so we're going to have a 1y double prime, plus 1r, so plus 1y prime, and then minus 12. So minus 12 times y is equal to 0. So this would be a differential equation which has that function as its general solution. Now let's look at some other examples. What we've been looking at is finding the general solution of these types of equations. Let's say that we consider next an initial value problem, where we pair our differential equation with a set of initial conditions. So in this example, we are asked to find the solution of the initial value problem, y double prime plus 4y prime plus 3y equals 0. So here we have a second order linear homogeneous equation with constant coefficients. And just like for first order differential equations, we had an initial condition given by y at some time is a given value or known value. For second order equations, we have a set of two initial conditions. We need the initial value of y, let's say y at time 0 is 2, and we also need the value of the derivative at time 0. Y prime of 0 is given as -1. And then once we have this solution, we are asked to plot the graph of that solution and describe its behavior as t increases. So let's take a look at it. As soon as we see that we're working with a second order homogeneous linear equation with constant coefficients, we know that our solution technique is to consider a solution of exponential form. Let y be of the form e to the rt, which means that r is a root of the characteristic equation 1r squared plus 4r plus 3 is equal to 0. And here to solve for r, we could factor. This factors as r plus 1 times r plus 3 is 0. And therefore our roots are -1 and -3, two distinct real numbers. So in this case, we know that our general solution, y of t, is given by c1 times e raised to the -1 times t plus c2 times e raised to the -3 times t. So the next thing I want to do is to try to apply my initial conditions to solve for the constants c1 and c2, these arbitrary constants. So notice here that we have not only an initial condition for the function y at time 0, but also the derivative y prime at time 0. So if I want to make use of that second initial condition involving the derivative of y, well, I'm going to need to find my derivative, y prime, of this general solution. So by the chain rule, our derivative would be -1 c1 e to the -t power minus 3 c2 e to the -3t power. And now we can apply our initial conditions. Y at time 0 would be c1 plus c2 which I was told has to be 2, and y prime at time 0 is negative c1 minus 3c2, which I was told has to be negative 1. So to solve this system of equations for c1 and c2, well, I noticed that if I add them, the c1 terms cancel, and I'm left with negative 2c2 is equal to positive 1, and so c2 is negative 1/2. Now, once I have the value of c2, I can substitute into one of my earlier equations. And the first equation told us that c1 is 2 minus c2. So since c2 was negative 1/2, we have 2 plus 1/2, or 5/2. And once I have these constants, c1 and c2, well, I can substitute back into my general solution, and we obtain the general solution. Y of t is c1, which was 5/2, e to the negative t, plus c2, which was negative 1/2, e to the negative 3 times t. So this would be our solution of that initial value problem. And here to describe our limiting behavior, well, we saw that both of our roots, r1 and r2, were negatives. So our two terms, these two exponential terms in our solution, are both exhibiting exponential decay, which means that as t becomes large, y of t is going to approach 0. So really, we knew what our limiting value was as soon as we saw that both of these roots are negative. As soon as we see both roots are negative, we know right away that our solution is going to tend to 0, and we can verify this result by plotting. So here in the notes I give a graph of my solution. We see that at time 0, our function takes a value of 2, so it agrees with our first initial condition. Y of 0 has to be 2. And the slope of the tangent line to this curve at that point does appear to be negative 1, the value given by our second initial condition. And as t increases, well, we can see that our solution curve exhibits exponential decay. And the larger that t becomes, it seems that we're closing in on 0, as expected. So let's look at another one of these. In this next one, we're asked the same sort of problem. We want to find the solution of the given initial value problem, y double prime minus 3y prime equals 0. So this is second order linear, homogeneous, and it has constant coefficients. And we're pairing this with two initial conditions. We know the initial value of y and its derivative. So solve this and then again plot the graph of our solution and describe the behavior of our solution as t increases. So same approach here as in our previous example. We're going to seek solutions of exponential form, y equals e to the rt, which means that r has to be a root of the characteristic equation 1r squared minus 3 times r is equal to 0. And again, here I can solve by factoring. If I factor out an r, I'm left with r minus 3 is 0. So two options, either r is 0 or positive 3. So at this stage, as soon as I see that one of my roots is positive, I know that my solution will be tending to either a positive or negative infinity, because I'm going to have an exponential growth term. So let's see which one here. I have my general solution, y of t, given by c1 times e to the 0t, which is just e to the 0, or 1. So I have c1 times 1, plus c2 times e to the 3 times t. And in order to apply my initial condition, I need to find the derivative of this general solution, y prime of t. So the derivative of a constant, c1, just gives me 0, and then plus 3c2 e to the 3t power. So once I have my general solution and its first derivative, I'm ready to apply my initial conditions. So if we substitute 0 in for t, my general solution would be c1 plus c2, which I was told has to be negative 2, and y prime of 0 would give me 3 times c2, which I was told has to equal 3. So it follows right away from the second equation that c2 has to be 1. And then again, using my first equation, well, we know that c1 is negative 2 minus c2. So if c2 is equal to 1, then c1 is negative 3. Now, substituting those constant values back into our general solution, we have y of t is given by c1, which was negative 3, plus c2, which was 1, times e to the 3 times t power. So this would be our solution of this initial value problem. And then to describe our limiting behavior, well, as t becomes infinitely large, we said y of t will approach either positive or negative infinity. We found that the value of c2, the coefficient for this exponential growth term, is positive. So y of t will be approaching positive infinity. And we can verify our result by sketching the graph of our solution. If we plot this solution, our initial value at time 0 is negative 2. And then as t increases, we have exponential growth by that factor e to the 3t. So the larger that t becomes, the larger our solution becomes in the positive direction. Okay. Now in this last example, we've got a problem where one of our initial conditions is some arbitrary value, and we want to know what specific initial condition will give us solutions that behave in a particular way. So let's consider this. We are asked to solve the initial value problem for y double prime minus y equals 0 So again, this is a second order linear equation, which is homogeneous and has constant coefficients. And we have initial conditions of the form y of 0 is equal to 2, and y prime of 0 is some value beta. And the question is, once we find our solution, what is the value of beta? We want to find beta so that our solution will approach 0 as t approaches infinity. So let's take a look. As soon as we see that we're working with a second order linear homogeneous equation with constant coefficients, we know that we're going to look for a solution of exponential form. Something like y equals e to the RT power, which means that r has to be a root of the quadratic characteristic equation 4r squared minus 1 is equal to 0. So we could either solve by factoring, or if I add 1 to both sides and then divide by 4, r squared is 1/4. And then we can solve directly for r as positive or negative 1/2. So here we have one positive root and one negative root. And so right away when we see that one of our roots is positive, we would expect that our solution will approach either positive or negative infinity, depending on what our constants are. But recall, for this problem, we're going to try to find a particular initial condition, the value of beta, which will make our solution approach 0. So let's see how we can accomplish that. Once I have found my roots, and I see that they are two distinct real values, that means that my general solution, y of t, would be of the form c1 times e to the positive 1/2 times t plus c2 times e to the negative 1/2 times t. And if I differentiate this expression in order to apply that second initial condition, we have 1/2 c1 e to the t over 2 power minus 1/2 c2 e to the negative t over 2 power. So once I have y and its derivative, I'm ready to apply my initial conditions. I can substitute 0 in for t in the general solution, which would give us c1 plus c2. I'm told that value has to be 2. And my derivative, y prime, evaluated at t equals 0, gives me 1/2 c1 minus 1/2 c2, and I was told that needs to equal this value beta. So there's a number of ways I could go about solving for c1 and c2. When I look at this, what I don't like about the second equation is that it involves the fractions, 1/2 c1 and 1/2 c2. So if I were to multiply my second equation by 2, I would have c1 minus c2 is equal to 2 times beta. And then if I were to add that to my first equation, I see that the c2 terms would cancel. So I find 2c1 is equal to 2 plus 2 times beta, or dividing through by 2, c1 is just 1 plus beta. And then I can solve for c2 by using one of my earlier equations. Say if we use the first equation, I know that c2 has to be 2 minus c1. which would give me 1 minus beta for my C2 value. So once I have my C1 and C2 expressions, I can substitute them back into the general solution, and we find that y of t is C1, which is 1 plus beta, times e to the positive t over 2, plus C2, which is 1 minus beta, times e to the negative t over 2. So this would be my solution in terms of that arbitrary value beta that I'm given for y prime of 0. And we want to then find the value of beta, which will make our solution approach 0 as t becomes large. Now here, as time t becomes infinitely large, our solution, y of t, is approaching, let's look at it term by term. We have 1 plus beta times e raised to a positive power. So that exponential term is going to approach infinity unless we get rid of it altogether by making this 1 plus beta value equal to 0. And then our 1 minus beta times e to the negative t over 2 will approach 0 because we have exponential decay for that term. So here our function is approaching something like 1 plus beta times some number which is becoming infinitely large. And the only way to ensure that we get a 0 limit there is to take our beta value as negative 1. If beta is negative 1, then this first term, which involves the exponential growth, disappears altogether, and we're only left with the exponential decay term, which guarantees that our solution will approach 0.